All right, let's get a seat. Let's talk briefly about the exam. Some of you did very well, others didn't. You can expect the next exam to be very similar to this one. 20 points or so, multiple choice, and the rest free response. And the last page will be exactly the same. Some folks did extremely poorly. I think some of you, for whatever reason, were shocked. I'm going to make a suggestion. The last question, folks, is a gift. Sometimes you need a little bit of a confidence boost. My suggestion is either the very first thing you do is go to the back page and get 4 or 6 points. Do the multiple choice where you've always can circle something, and then go to the last page. I had somebody tell me that they went to the first page, they did the multiple choice, and then they got the problem 12 and couldn't do it. So I thought, I'll come back to problem 12. And they looked at problem 13, they couldn't do 13, and 14. By the time they got to the last question, they couldn't do it, even though they probably knew how to do it. Okay? Time management's important. I walked around this room watching people, and you were spending way too much time on the multiple choice. Okay? The exam was 70 minutes long, which means, you need to spend about a minute or two for every point. You need to spend a minute for every 2 points. So what that really means is the multiple choice should have taken you 10 to 15 minutes. And I saw people who I was watching, and 20 minutes in, 25 minutes in, they were still working on multiple choice. There was nothing in the multiple choice, folks, that required you to do calculations that should have taken any more than a minute or two. I mean, some things you should have been able to do in 30 seconds. So time management. My exams, folks, believe it or not, the exam was shorter than I'd planned by 3 questions. Okay? I got rid of 3 questions, 3 free response questions. Okay? Now, some of you, once again, I have to write an exam, folks, that challenges everybody. Okay? Somebody got a 99 on the evening class. They missed a minus sign, and it was sort of a cheesy minus sign. So they really could have gotten 100%. There were some 96s in this class. So I have to challenge the best students. But I was really bothered by the fact that there were scores 8, 9, 10, 15, 18. Scores like that indicate to me that either you're not coming to class, you're not understanding much, if anything, or you're not studying the right things. So I'm going to switch things a little bit. I'm going to do more problems in class, okay? So I tried this last night, okay, since I practiced on the night class than you guys. That's probably why you did 10 points better than they did. Their average was 45, but they had a 99. So last night, I'd planned my lecture to have less of me talking, more of you people actually thinking and working. And you know what? There were people texting. I mean, it was when I said, do this problem. And they were not using their phone for a calculator. So folks, if that's how you're going to approach this class, you're bound to not do as well as you could if you really focused. So if you do not bring a calculator to class, you're a fool. Okay? I told you that on day 1. Okay? the best way, folks, to learn how to do these problems is to not just listen to me, but it's to actually do the problem. Instead of listening to me and then you go, yeah, I think I get that. Then what happens is you don't get it. So I'm going to try and do more examples. That'll certainly be the case when we get to Chapter 8 later today. There are some things in Chapter 7 where we're going to do some examples. We're going to finish up Chapter 7 now and move on to Chapter 8. Okay? In terms of reading, okay, finish 7, the last half a dozen or a dozen pages where we talk about bond enthalpies and things like this, and then read the first maybe 10 or 15 pages of Chapter 8. Discussion questions this week, for at least the first part of the week, we're going to be going over the exam. Now, unfortunately, you don't have your exams. Okay, I have no idea, I have no control. We got your exams to the scanning place at about 10 o'clock on Friday morning. Okay? The problem is they had 819 exams from me, for my 2 classes, and then there were other classes. And so I have no idea. I'm hoping that you get your exams. You know, I guess you'll be notified. I'm not really sure how you are notified, but they put them in a Dropbox. They put them in something so you can, in a PDF format, you can download them and print them up. That's the best way to go about doing this. Do that and go to discussions, folks. Go several times. Okay? It's better if you had your exams. I'm sorry you don't have them, but okay. Any questions about the exam? If you got an 8 or a 9, people ask, can I still pass the class? The answer is absolutely. Okay? So what if you got what's an F on the first exam? Do better and better and better, and you're going to pass the class. Okay? That's all there is to it. You cannot continue to score below the mean, though, and expect to pass the class. I mean, that low below the mean. So I don't want anybody to feel like they are in a situation where they cannot pull themselves out because they did so poorly. It's not true. Okay? I can look for improvement. Okay? The final is worth 200 points. If you know what's on the final and you do well on the final, that tells me you know what's going on in the class. I might bump your score up a tiny bit. Okay? So don't anybody give up. But if you're not going to discussions, okay, if you're not bringing a calculator class and doing the problems here, and if you're not doing the problems, I had some knucklehead email me saying that it's not that it's my fault, but it's sort of my fault because I told you not to bother studying the sampling stuff. And that all the free response questions were straight from sampling. And I thought, holy moly, I didn't even look at sampling. You know? I mean, I told you folks that I think I told you, the only real free response question I could ask from Chapter 5 was a density kind of a question. Okay? I said, okay, you know, there's the unit cell, you know, there's 1, 2, 3, or 4 atoms per, in a face-centered cubic or whatever. That kind of question I said would be on the exam, and it was. And the only other thing was a density one, where you had to know how many atoms were in a body-centered cubic or a face-centered cubic or something, and then you did the problem exactly as we did in class. But I was nice enough on the exam not to give you kilograms per meter cubed. I gave you what density is usually in, grams per cubic centimeter. And people just blew that question. So we went over problem discussion question 7-20. Okay? People bombed that one. I did that in class. So there were several things, folks, that I took right from the book, right from discussion questions, and it should not have been a surprise, and yet it was a surprise. During the exam, I actually had people asking me if they were required to know the boiling point of water. There was a question, you know, the one that said it's at 25 degrees C and you got to warm it up to boiling and then you got to have the vaporization, and how much heat does it cost, or how much energy do you have to put into it? And people in both classes asked, how am I supposed to know what the boiling point of water is? If we weren't filming right now, I would swear, okay? Really? And I guess you don't know what temperature things freeze at. Okay, there's certain things, folks, you just have to know. You know? I mean, so you're screwed. You are screwed. If you do not know what the boiling point of water is. I don't expect you to know what the heat capacity of water is. I gave that to you. But the boiling point? You know? People who said I didn't give enough information, this periodic table here, it's got numbers on it. Okay? It's called the molecular weight. Somebody says, well, I don't know how to figure out moles from this. Another person asked me, during the exam, do I convert this from grams to moles? Well, I would, because I'd convert everything to moles, but that doesn't mean that's the right thing to do. People, you got to practice, 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 so that nothing is a surprise to you. There was not any surprises on that exam that I can think of. You know? Who's got a question? Somebody say question? Yes?
Did we even talk about combustion or was it on the test?
Did we talk about it? Absolutely did.
Did you do any practice problem with that?
Well, I did one in class. We're going to do more today, but I told everybody, I said, folks, combustion means you burn it with free oxygen and you make carbon dioxide and water. How many remember me saying that? Yep. That's combustion. So I don't have to tell you anything. If I say you combust this, okay, right now, do this problem. Do this problem. If I combust 32 grams of methane, methane is CH4, 32 grams of methane, I combust it. How much water do I make in grams? How many grams of water do I make from combusting 32 grams of methane, CH4? How many hydrogens in methane? Okay. How many hydrogens in water? So how many waters am I going to make for every methane I burn? 2. Okay. What is the molecular weight of methane? Carbon is 12, hydrogen's 4, 16. 16 plus 16 is 32. How many moles did I say you had? I said you had 32 grams. 32 grams divided by 16 grams per mole, 2 moles. You got that? 2 moles. So how many moles of water did I make? Yes. So if you got 4 moles of water and it's 18 grams per mole, how many grams of water do you make? 72 grams of water. Who said 4 moles? Who asked that? Well, how many moles of methane did we start with? 2 moles of methane, and there's 4 hydrogens. So you know that that methane is going to yield, every time you burn a methane molecule, you make 2 waters. Folks, this shouldn't be a surprise. This is the kind of thing that you should be able to do boom, 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 boom. But that's combustion. Who still doesn't know why we get 72 grams of water? But it's this quick. This is a kind of a question, folks, that I could ask on multiple choice, and the amount of time we spend on it is about the amount of time I would expect you to spend on it. Do this. If you cannot see the board, folks, because you're too far in the back, move up front. Yes?
On the test, it didn't say whether the combustion of that one compound produced liquid water or vaporized water. So, like, were we supposed to just know that it was...
Okay, so his question is that if, So you sure it didn't say?
Yeah, sure. It didn't say liquid.
Okay. I'm not sure, then I'll have to look at that. Somebody have an exam? You printed up the test stuff? Okay, well, I'll look into that. So yes, the question is that how do you know? Okay, so here, we got liquid, so I'm giving you the liquid and I'm telling you what it is for the liquid. The question is, he's saying, so how do I know it's liquid or gas? And I'm not sure what the question was. I'll look at this while you guys work on that. Thanks.
You gave the heat of formation of liquid water.
I gave you that. Well, then you got to figure that's all you got is liquid water. Yeah, okay. Thanks.
I thought maybe you had to add in like
No. If you don't have to, if I don't say that, if I said I want to know what it is for gaseous water, then I have to give you something. Okay, do this problem. Who's got an answer? How many water molecules are we going to make for every benzene that's burned? 3, right? There's 6 hydrogens there. So you're going to make 3 waters. Now, what do we need to do? How do you write this thing? Okay? It's going to be C6H6 plus O2. Goes to CO2 and H2O. Okay? That is a combustion. We went over it the other day. That's a combustion reaction. How much water and CO2, I don't know. How much oxygen, I don't know. But I know that you write it originally down just as C6H6 plus O2 goes to CO2 plus water, and then you start to balance. How many got that? How many didn't get that? Okay, look, there's like 16 hands that went up the first time, so how many did not get this? How many did get this? Okay, good. Still not many. Folks, if you are having trouble balancing that equation, okay, as a combustion equation, you better go back and read from the beginning of the book, okay, on how to balance equations. I'm not trying to sound like a jerk. I'm just saying there's you know, I can't spend a whole period just on how to balance equations. That's Chem 1A. How much heat is released per mole of benzene? Here are your heats of formation, CO2, and the heat of formation for water, and heat of enthalpy of formation for benzene. Okay, how many got that? Okay. Is that the answer? No. The question, folks, is how much energy to burn 1 mole of benzene? How many moles have we got here? 2. So we're going to divide this number by 2. There we are. Folks, that's an 8-point question on an exam, which means you should spend, you know, 5 to 7 minutes on it. If you cannot do this in 5 to 7 minutes, then you need to practice, practice, practice. So do we understand combustion? Yes?
Since it says how much heat is released, do you need the negative sign? Or should you leave it off?
Well, so that's, you're right. This would be more like this is going to be the delta H. Okay? So you get it right with this, or if you said 3,266 kilojoules was given off. I mean, I don't need this kilojoules per mole, actually. Okay? So it's a good question, because once again, we tend to think of things when it just says how much heat. If I said what is the delta H for this reaction for 1 mole, then you would need to have that negative sign. You get it right either way. Okay. The notes, folks, for today's lecture have already been posted, I hope. Or they're being posted right now. So you should, you need to download this stuff and go over this. Okay, another thing, Hess's law. How many are confused with Hess's law? Oh man, last night everybody was. Okay. So, do this one. Okay? Make use of the table to calculate the delta H for the following reaction. Okay? Do it. Don't watch me do it. Do it. Okay, how many don't know what to do with this? Okay. So what is it? What did I look at what this says right here? What does that say? Combustion enthalpies. So what does that mean? That means when you burn this, you get off this. When you burn this, you get off this. When you burn this, you get off this. So write your combustion reactions right here. You should have 3 of them. How many did not get this? When it says combustion, you burn everything. And you only have 2 products, CO2 and water. We're assuming a perfect burn. You cannot do this problem if you don't get these right. So how many got it right? How many actually got these 3 reactions? How many didn't? How many didn't because you don't have enough time? Okay. I'd rather it be that you don't have the time. So these are the 3 equations that you need. Okay? Hess's law then becomes sort of a crossword puzzle. Okay? You have all the information you need here. It's just not always on the right side and the right size. Okay? Look at the original equation. C4H4, is that on the products or the reactant side? Reactants. H2, products or reactants? C4H8, product side. Okay, so are we okay with this one? It's on the product, on the reactant side. And we're okay with this one. It's on the reactant side. You understand what I mean by products and reactants? The only equation that is backwards is the middle one. Okay? So what do we have to do to make this guy end up over here? We flip everything. Flip everything. This now goes over here. You got, so it's going to be 4 CO2s plus 4 waters goes to C4H8 plus 6 O2s, and then you make that a positive sign. When you flip an equation, it's just the opposite. So this becomes a plus right there. Yes?
Why isn't the last equation multiplied?
Hold on, we're not there yet. Okay, he knows, I made him do it in class, so I know he knows what we're doing here. So, okay, so you're right. Let me get to the next slide. You want to come down and do it, Luis? You did a good job the other day. Okay. So, here's the equation that you were given. Okay? Here's the equation you were given, and this is what we want to make. This is on the wrong side, and as he points out, wait a minute, you need 2 of these. You see that? You need 2 hydrogens, not 1. So this whole thing needs to be multiplied through by 2. So you end up with this. Okay? And over here, I have made this a positive, and I multiplied this whole thing here by 2, because I have 2 hydrogens that I need. And then, folks, you draw a line right here. Okay? Draw a line right here, and you start crossing stuff off. If you've got something on the left side, and you got something on the right side, you can cross it off. Okay? So how about you? How many oxygens on the left side up here? So I see 5, 6 on the left side. You, this lady right here behind her, this lady, yes, you. How many on the right side? 6. So your oxygen just cancel. You just go boom, boom, boom. Okay? How about waters on the left side? 4 waters here. 2 plus 2 is 4. Perfect. Get rid of that. CO2s. There's 4 CO2s on this side. There's 4 CO2s over there. Get rid of that. You should actually be crossing these off on your paper, okay? And what you're going to find is what you're left with. C4H4 plus 2 H2s goes to C4H8. That's it. There's nothing left. And then you add all these things up, and this is the value you get. This 2341 plus 2755 minus 2 times that, which gives you that, minus 158 kilojoules. Okay? Minus 158 kilojoules is the delta H of reaction for this, oops, I don't have it. For the C4H4 plus 2H2 goes to C4H8. If you don't know what combustion is, folks, you can't do this. Combustion is the key word that says Don's being stingy and he's not giving me the equations. Okay? I can do that. Yes?
When you give us the enthalpies of combustion,
Yes.
are you going to, my question is it the energy per thing combust, per mole of thing combusted?
Yes. Per mole. Okay. Do you feel any better about Hess's law? Okay, this, folks, is on the web. Do it, do it, do it. Practice this stuff. Because, folks, very likely, exam number 2 will have a Hess's law on it, certainly some combustion something or other, and it'll certainly be on the final. So don't think that, oh boy, I get a Hess's law, I won't have to see it again. You will certainly see it again. All right, change gears. Something you haven't seen before. It's near the end of chapter 7. It's called bond enthalpies. So bond enthalpy is how much energy it costs to actually break bonds, okay? Energy it takes to break a bond. So here we have an H2 molecule. It's happy, very happy being H2. O2 is very happy being O2. So you have to put in some energy to break it apart. The energy required to break an H2, a mole of H2, into a mole of two H's is 436 kilojoules. The energy it takes to break an OO bond is 496. The energy it takes to break an OH bond is 496. I wish they weren't the same, but they are. So one way to estimate how much energy is given off in a reaction is to just tally up all of the bonds that are broken and all the bonds that are made. Okay? So, do this one right here. What is the delta H of this reaction right here? So I'm burning. This is a combustion again. Okay? H2 combusts. Okay? How many have ever heard of the Hindenburg? Okay, I think it was on the exam. Okay? This was their downfall, was that hydrogen burns. Okay? H2 gas burns with O2 making water. So I could have asked you, I could have just given you this information and said, okay, I want you to figure out what is the delta H for this reaction using only bond enthalpies. So, look up here. It costs 436 kilojoules to break up 1 mole of H2 into 2 H's. We understand that? So how much is it going to cost to break up 2 moles? Twice that, right? There's a 2 right there. How much energy is it going to cost to break up a mole of O2? Well, it's 1 mole is right there, 496. Okay? And over here, you're not breaking this up though, are you? You're making this. How many OH bonds are there in 2 molecules of water? Yeah, each water molecule has 2. If this is the oxygen, 1, 2. Then there's another water, 1, 2. So you have 4 of these, okay? But you're not breaking them, are you? You're making them. Okay? Now, bad news is this. Bond enthalpies are always positive here, okay? It always takes energy to break a bond. So this is the one time that it's not products minus reactants. I'm sorry. In this case, it's reactants minus products. Okay? So here's the reactants. 2 times, so we agreed that the hydrogen, the H2, which costs us, we have to put in 436 kilojoules per mole, and we had 2 moles, so it's 2 times that. This was the amount of energy it takes to break a mole of oxygen bonds. And then minus the products. There are 4 OH bonds, and each OH was 496, so it's going to be minus 4 times 496. You get a minus 616. So what's going to reactants minus products because all bond enthalpies are positive. So that, folks, is the amount of energy that's given off. Yes?
What if it's like, what if the reaction was flipped? Then isn't it bonds broken, bonds formed?
If it's flipped.
If the reaction was the opposite, like the water breaking into oxygen, hydrogen.
Okay, then it would be a plus 616. Yeah. Yeah, anytime you do just the opposite, it's always just a negative sign, yeah. So this is bond enthalpies, folks. Look at this. That's the table. You don't have to write it down. This is a kind of table that you will be given probably on the final. It'll be on the periodic table page. And it is from this that you will then calculate certain reactions. Okay? So these are bond enthalpies. Notice that how they're all positive. So you're going to have to know how to do it. So this is just sort of this is from your book to show that it doesn't matter. You can, if you've got a way of going from here to here, this energy difference here is the same as the energy of the reactants minus the energy of the products. Okay? So delta H formation is equal to the energy of the reactants minus the energy of the products. This is in your notes. This is just something that's a reiteration of what I just showed. Once again, energy getting bigger as you go this way. So something like this that has products down here means that energy was actually given off. This is a more stable form. And the difference between here and here is the delta that's given off. Okay, that's given off as heat. So, or I could give you this table. Okay, these are just some examples of some carbon, hydrogen, oxygen bond type things. Okay, and we say average because it's an average. Okay, not every one is exactly accurate on here. So, the polymerization of ethylene to polyethylene. So here's what we're doing, okay? And I want to know whether it's exothermic, isothermic, or exothermic, okay? So, how many carbon-carbon double bonds are there? How many do you see? Carbon-carbon. 1, 2, 3. Okay, so we are going to have to break 3 carbon-carbon double bonds, and then we will make 1, 2, 3, 4, 5, 6 carbon-carbon bonds. Okay? So we're breaking 3 carbon-carbon double bonds, and we are making 6 carbon-carbon bonds. So remember that, 3 and 6. So now, oops, I don't want to do that. There. Do the problem. The polymerization of, let's say, 3 ethylenes making 1 polyethylene. So you're breaking 3 carbon-carbon bonds, you're forming 6 carbon-carbon bonds. Sorry, 3 carbon-carbon double bonds, and you're making 6 of the carbon-carbon bonds. So here's the information. There's a carbon-carbon double bond, here's a carbon-carbon single bond. What's the answer? So you've got 3 carbon-carbon double bonds, okay, 3 times that, and then you've got 6 of these bonds here. Is that what we got? That's how you use bond enthalpies, okay? If you don't understand it, read about it. This is in the notes. So once again, here's the energy you had for single bonds are this much, and then you got twice as much of those, okay? So you multiply this by 2, you get a number that is bigger than that. That means that that it's an endothermic reaction. It actually takes energy to make this happen. I said exothermic or endothermic? Okay, did I just say that backwards? Okay, you get this much off, so you multiply this by 2, this number is bigger than that, and therefore it's exothermic. Sorry. Okay, now, this is from your book. Okay, could very easily show up on an exam. So what we're doing is it says estimate the enthalpy of a reaction between the gaseous iodoethane and water vapor. So here we have iodoethane, and here's water vapor. And we end up making ethanol and HI. Okay? Write that down. So write this down. C3H, CH3, CH2I gas plus water gas goes to this. All right, so we're making this molecule into this, okay? Do you see a CH3, CH2 on the left side? Do you see one on the right side? So you don't need to do this. Okay, you can if you want, you can go onto the enthalpy table, and you can say, okay, I've got, let me see, in this case, 5 carbon-hydrogen bonds. Break those. You got a carbon-carbon bond right here. Break that. You can break this apart, okay, and then you can form these. Or you can say, well, why do I need to do that? This whole part of the molecule is the same from here over as it is from here over. So all you're really doing is breaking a carbon iodine bond and making a carbon OH bond, and then you're making an HI bond and water, okay? So now go to the table and do it. So that's why I wanted you to write the equation down. So here's a carbon iodine bond right there. You're not breaking any of these guys here, okay? Here's your OH right there. Okay, just keep working. I've just done it for you here. Yes?
Why is it that for the reactants you're only breaking 1 mole of H2O?
Because I'm lazy. So you got, because you're making one here. Yeah. I mean, that's a bit of a trick. That's why I said why only, one of these instead of 2, because once again, we're not breaking that OH bond, we just have an OH bond here that we're breaking. So, you got it? Makes sense? Good. Okay, we're at the end of chapter 7. There are different things that we refer to in terms of enthalpy of solution. Okay, if I have some water and I put some salt in it, is there going to be energy given off? Is it going to cool down? Is it going to warm up? That type of thing. So this is just a table. Heats of solution. Okay, so this means that if I put in some lithium chloride into water, I'm actually going to get some heat out. Okay, if I put calcium chloride into water, I get a whole lot of heat out. If I put sodium chloride in, it takes a little bit of energy. So if it takes a little bit of energy, what happens to the temperature of the water? Drops a tiny bit. Okay, KCl drops even more. Sodium nitrate drops a lot. So we got a lady here in the front who's got an ice pack on her leg. All right. How many of you have ever had one of those bags that you punch and then it gets cold, like some sort of an athletic thing or something? Raise your hands. Okay. Do you ever wonder how that happens? Because of this right here. Sodium nitrate. Look at this. It sucks up that much heat per mole. Okay? So what you do is you got water in the bag and you got this sodium nitrate in the bag, or these ammonium nitrate. You punch it, breaks it so that it mixes the two, and all of a sudden the reaction actually sucks up a lot of energy and actually makes the water colder. Okay, that's how this works. That's because this is positive. Up here, folks, this is what you want to put on a road. Okay, you put some salt like that on a road and it all gives off heat. It's not the only reason. It actually lowers the melting point of water. But that's a reason why you would put something like this with a very large negative delta H of solution on melting ice, or trying to melt ice, and then you would use something that has a very big positive. Now, you can't get too positive. Okay, you can get big negatives, but you can't get, because it's just not going to happen. Okay. This is, you got to put a lot of energy in to get this to go. And this is just a schematic to show how this works. You start off with sodium chloride as a crystal. You can do this. The lattice energy is actually 788 kilojoules per mole, and the solvation energy is 784. So 788, 784, this is a tiny bit higher, so that the delta H of solution is 4 kilojoules per mole. You can, however you want to do it, you can do it. But what that means is you got to put a tiny bit of energy into the water to have this thing fall apart. So once again, this is just called the heat of solution. So just add them together. 788 minus 784, 4 kilojoules per mole. We're done with chapter 7. Yeah, nice try. Jeez, you guys. I can't believe that you should just be so excited to get out of chapter 7. The first law wasn't nice to you. Maybe the second law and third law will be. This is posted. Who can go online right now? Okay, I'm not going to be irritated if you do this. Somebody go online right now, you. Only him. I just want to know if the class notes are posted. I sent Barb the email at about 9 o'clock with the 2 lectures. So I just want to know if they're posted. Sometimes the files are so big that she doesn't get them, and it may be after class that we post them. They're not? They're not posted, huh? Okay, well, they will be. Okay. I sent them. All right. These are also posted. Okay, read this. Okay. I'm tired of talking. I got a sore throat. All right, spontaneous. What does it mean to you? Okay, if somebody is a spontaneous kind of person, what does that mean? It means they do things quickly and maybe without much thought, okay? Spontaneous, folks, is a relative term, okay? If I take an ice cube and I put it on this table right here at the beginning of lecture, and it's just a regular ice cube that I bought from Albertsons, what's going to happen to that ice cube during my lecture? It's going to melt, okay? That's called spontaneous. That's a spontaneous event, okay? And it happened, you know, in maybe 20, 30, 40 minutes, okay? So spontaneous in that case is one lecture. But things like rust, you can see rust. You can see a nail that's rusted, but you can't watch stuff rust. How many of you have ever eaten an apple and noticed how kind of the apple, if you don't eat it kind of fast, the white part of the apple gets a little bit brown? Okay, well, that's actually oxidation also. That's rust that's forming. Okay, there's iron in the apple, and with the solution of the apple core, it makes it so that it rusts a little bit quicker. But normally rust takes a long time. Okay, still, you know, long time for you folks who are teenagers mainly, you know, is like 30 seconds. Okay, a long time for an old guy like me could be days or whatever. Okay, so spontaneous just means it's going to happen. Okay, it's going to happen without there being much, if any, influence from outside. Okay. The second law of thermodynamics tries to help us understand why certain things are spontaneous and others aren't. Okay, some things aren't spontaneous. Okay, if I were standing right here at the bottom of the stairs and I fell forward, I would end up right here. Okay, if instead I were at the top and I fell forward, it's possible I could end up down here. Right? I mean, it would be very painful. But but the chances are a lot better. Okay, question. Better odds of me ending up down here if I start at the top, or better odds if I start at the bottom and I'm going to fall up to the top? Right? So the point is that me falling down the hill, or if I took a ball and I kicked it a little bit and it rolled down the hill here, that the ball would end up down here, pretty good chance if I kicked it not too hard and just like this and let it boom, 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 boom. If I stood here instead and kicked it this way, what are the odds of it making it to the top of the hill? None. Spontaneous down, non-spontaneous back. Okay, that's what we're going to learn about. Why things are spontaneous and why they're not. So this is just a picture. This is just a block of metal when it's really hot, and then it cools. Okay? Just like the ice cube. You set it there on the table. If it's not burning up the table, it just slowly cools down because of what the atmosphere is doing to it. Okay? It's spontaneous. It spontaneously cools because it's hotter. Okay? It's hotter and the energy flows from it to cooler. Hot to cold is how things work. Hot to cold. So you put it right here, slowly cool down. I would not take this chunk and put it here and have it instantly just heat up. One's reversible, one's not. If you were to go into my lab and we had a bulb here that had air in it, just air at 1 atmosphere, and in here we had some other gas that was at 1 atmosphere also, same no pressure difference, but there's a stopcock between them, and this one has some color to it. If we open up that stopcock after a while, not instantly, okay? Spontaneous doesn't mean instantly. But after a while, the molecules up here would mix down here, and the ones up here would mix like that, and you'd end up with this. It would just happen. Molecular motion, boom, 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 boom. They run into each other, and eventually they're evenly distributed. The opposite will not happen. I can't have this like this and then come in the next morning and find it like this. Statistically, that's not going to happen. Okay? If I have one molecule If I start with one molecule here and none there, then there is a chance. There's a 50% chance that it's going to be here or here. Let's say they're the same volume. With one molecule, it's either here or here. So yeah, sure, it could be there. If I had two molecules, you know, there are going to be times when they're both here and they're both here or they're both spread out. But the more you have, folks, the less likely it is that something like that's going to happen. And that's a field we call statistical mechanics. So, I want a big yes or a no. Water runs downhill? Yes. A lump of sugar dissolves in a coffee? Yes, unless it's supersaturated. 1 atmosphere of water freezes below 0 degrees C. Some of you aren't going to know the answer to this. But the answer is yes. Heat flows from hotter. This is something that a lot of you, it's not obvious, but things go from hot to cold. They don't go from cold to hot. Okay, it's hot to cold. So if I put this in a warm soda in the refrigerator, the warmth of this comes out, hits a molecule of cold air, and transfers the heat to the cold molecule. It's not the cold transferring it this way. It's heat being drained out. It's not cold coming in. Okay? Do we agree with this one? Although I think I've done that. Gas expands, blah, 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 rust iron, okay. So, a spontaneous change need not be, I can't read this, fast, and in some cases must be, okay, here we go. We already did this problem a little earlier. Hydrogen, what is this called right here? Combustion, thank you. Okay, it's combustion. It's a spontaneous thing, but you know what? If I have oxygen and hydrogen together, they don't combust. I could have, if this had oxygen and hydrogen in it, I could keep it here for years and years and years and years. Okay? Sometimes you need that little kick to kick that ball at the beginning down the stairs, and then boom, 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 it keeps going. This is one of those. What do I need to add to this as a little impetus to move this direction? A flame. Okay? A flame, boom, and this thing ignites. Non-spontaneous can be brought about only by doing work on the system. Okay? I can get the ball back upstairs, but I got to walk it back upstairs, okay? I have to put energy in. I can make it go back up there. It kicks down and just boom, 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 comes down to me, but I got to actually physically put some effort into getting it back up there. Okay? So you can make something that's non-spontaneous go in the other direction. Okay, just like that skier. In the old days, folks, and I'm talking old days, I didn't know how to ski, okay? I kind of grew up as a poor kid, and so skiing was not an option. But I met this girl that I eventually married, and her family had a little bit more money. And so she learned to ski when she was younger. So she took me we were dating, yeah. I married her. So in probably 78 or 79, we went to Snow Summit, okay, up in the mountains. And they didn't have some of the nice stuff that they got now in terms of getting up the hill. They just had a tow rope. Anybody know what a tow rope is? It's just like this big rope like this, and it just goes up the hill. And you got to have gloves on, and you got to grab that rope. And if you don't have gloves, your hands get all these slivers in it. And then you get pulled up the hill. Okay, so here I don't know how to ski. And the only way to get to the top of the hill is to get pulled up on skis. That seems kind of harsh. So anyway, I fell several times just trying to get up there. But that's exactly how it looked going up the hill. You hold on, energy coming into dawn, and I'm just going right up the hill like this. And then it took me much longer to get down the hill. I gave a lot of energy to the snow that day. That was not fun. Okay, entropy. It's a key, folks. You got to know what this means. Entropy is huge. You'll find out just how huge it is. It's disorder. Okay? I look at this class right now, it's pretty ordered. people sitting in little, it's not like you guys are solids, okay? But in about 15 minutes, when it's time to go, all of a sudden become very disorderly. People come in and moving past each other like a liquid or a gas, okay? So nature likes disorder, okay? So low entropy means little disorder, like you as a class. And then high entropy would mean when you're leaving, okay? So let's say I have an ice cube. Put it right here. What is the sign of the change in entropy going from a solid to a liquid? Would you have more entropy as a solid or more entropy as a liquid? As a liquid. The solid is pretty ordered, okay? It's pretty ordered, so it has low entropy, okay? It has very little disorder. Once the thing melts, you know, it goes all over the table and has more ability to kind of move around, and so it is more disordered. The entropy of an isolated system increases in the course of any spontaneous change. So entropy always changes and increases when it's an isolated system. Randomness, disorder of system. Order goes up, entropy goes down. Disorder goes up, entropy goes up. The change, once again, we look at it changes. The change in entropy, we're back to, you know, product minus reactants or final minus initial. So the entropy you start with is subtracted from the entropy at the end. Okay? So if I have an ice cube, start with an ice cube on this table, that is the initial situation, and then I let it melt and it's water. So it's going to be the entropy of the liquid water minus the entropy of the solid. Okay? This is bigger than this, therefore this is a positive sign. The delta in this case would be positive. And that's what we like. We like positive entropy. So once again, if the final entropy is greater than the initial, then we end up with a delta entropy greater than 0. I just said this. Gases, holy smoke. So I have this ice cube that melts, got liquid, and then it evaporates. Okay, so first the ice cube was sitting in one spot that I could define quite well. Then it melts, kind of does this and blobs a little bit down the leg of the table. And then tomorrow or on Thursday we come in, there's no water here anymore. It's in this room. Gases have tremendous entropy. So gases, if you have a reaction that ends up making more gases than you started with, oh, that's wonderful. So solids, liquids, and then gases, gases, gases. This would be like a multiple choice question. 3 states of matter. Which of the following has more entropy? Solid, liquid, or gas? This is my analogy of the melting piece of ice. Okay? Processes that lead to an increase in entropy. Solid to liquid. Liquid to gas. Solvent. If I have something that is segregated like this would be like melting some sort of a salt, then it ends up like this. This has more entropy. There's more randomness in this than there is here, so entropy increases. And if something's warmer, the same chunk of aluminum or whatever is warmer, if it's warmer, it's got more entropy. Okay, so heat is important for entropy. All right. I'm going to save you some of the theory, okay? I think either I did a crappy job of explaining theory to you for Chapter 7, or you did a bad job of listening or something. I don't know, or both, okay? So I'm going to spare some theory, and once again, I'm trying to get you so you can do some problems and all. This, folks, delta S, the change in entropy, is equal to the Q reversible over T. That should be, I just didn't know how to make it under here. So that's Q over T. Q is heat, right? Q is heat. Q is the energy transferred as heat. T is the absolute temperature. Holy smoke, what do we mean by absolute temperature? What do we mean by absolute temperature? That's Kelvin, okay? No equations, folks, no equations in science that I can think of allow you to use Celsius. Sometimes you can get away with it if it's just a delta, right? Because if I say the temperature went from 25 degrees C to 50 degrees C, what is delta T? You'd say 25 C. Same thing as if it went from 298 to 323. What is the delta? 25 K or 25 C. So there are some times you can use it, but don't get lazy. Okay? You need it in K. So now my question is right here. What are the units for entropy? Look at that. Don't look it up. What is heat in? Joules. Joules per Kelvin. Thank you. So once again, the units for entropy are joules per Kelvin. So if we look at this equation, if Q is big, okay, that means a lot of heat was given. It's all heat, energy. A lot of heat was given, okay, then entropy is big. The change in entropy is big. What do I mean by this? Read that and tell me. I want to point to somebody and I want you to tell me what it means. At low temperature, you get more bang for your buck in terms of delta S for the same amount of energy put in. Why? How can I say that? Look at this. What is the equation? What's in the numerator? Heat, okay? We already said that if Q is big, then this is big. Well, how do we also make this big? We make this small, okay? So if you put in, okay, I think there's a problem, but let me just ask you. If you put in 100 joules of heat, 100 joules of heat at 300 degrees K, what is delta S? It's going to be 100 joules divided by 300 K. So it's about 0.3 joules degree, right? Who doesn't get that? Who needs help on that? Okay, once again, you just plug it in right there. If that's 100 joules and this is 300 K, then you got 100 over 300, you got 1/3 joules per K. All right? Do the same problem, but this time, same amount of heat, 100 joules, but this time it's at 100 degrees K. What's the delta S? 1. Right? Because this is now 100 joules and this is 100 K. Divide them, you get 1. So the delta S is 3 times bigger in this situation at 100 degrees than it is at 300 degrees. Okay? This is going to come up later and it's going to be very important. So you better memorize this equation, folks. It's going to be on the exam. Promise. Okay, we just did this. Sort of. This is the kind of question it could be. So you already know, this is 100 and this is 25. Now, can I put a 25 there? No. That's 298. T is always in Kelvin. If you put 100 here and 25 here, you're going to say delta S is 4 joules per degree, and that's wrong. Here it is right here. Easy? This is easy so far, isn't it? Good. This is just an example of solids, liquids, and gases. Once again, as you increase, the temperature goes up, go from a solid to a liquid to a gas, entropy increases. So you got the system, you got the surroundings, but unfortunately, folks, here the surroundings is more like the nearby surroundings. Okay? It's a little bit different than we've done in the past, where it's like either the system and then the universe. This is like the system and then the surroundings and then the universe. So it's a little bit, I'm not real comfortable with this. But anyway, so you got the surroundings, and then you got sort of the total is here. We're going to work through this. So look at this. Look at the top one. Heat goes in. This is a warm system. Heat goes in, entropy does this. That's how much entropy you get. In this case, heat goes in, same amount of heat goes in, entropy is bigger. Why? Because delta S is equal to Q over T. Okay, this T is smaller because it's the temperature. So it's the same thing that we did before. These are kind of boring, okay? So you can have, in this case, heat comes out of the system, entropy goes up. In this case, heat goes in. I can make entropy go down if I put in heat. I can get that ball back up the stairs if I put in energy, okay? But this is one where you actually have to put in heat, and then the entropy goes down. You can have them where the entropy, the total entropy, so the entropy for the system goes up, the entropy for the surroundings goes up, and then you got a nice big happy entropy. Or you can have one where the entropy goes down here, entropy goes up there. As long as you got a positive one, it's going to be spontaneous. Just download this. I can't make this very exciting. And this is just more of the same stuff. Okay. This is what your book gave me, folks. Don't you love that book? How do you like that? If you like math, okay, this, you'll love this. Area under the curve. Piece of cake. How many, raise your hand, how many think I should not go over this at all? Not. I'm not saying I'm not going to do the third law, but I'm not going to do the derivation. Is that okay with everybody? How many is it not happy? How many of you are really disappointed?
It's not going to be on the test, don't go over it.
What's that?
It's not going to be on the test, don't go over it.
It says if it's not on the test, don't go over it.
If it's on the test, go over it.
Well, I don't know if I like that attitude. Well, it's in your book, okay? I'm not sure. I mean, I could put that on the test. Now that you mentioned it, I wasn't going to do that, but maybe I should. Yeah, it's the guy with the hat. Okay. So look at this system right here. We got a bunch of red balls over here, and we got a gate, and then we got an empty one. And then we do that. More entropy or less entropy? More entropy. Look at we've got twice the volume. The reverse never happens. You're not going to get all these balls statistically on this side ever again. So here's an equation you must know. Entropy is equal to KB log W. KB is a constant. So for those who raised their hand that they were disappointed that I wasn't going to go over the derivation of the integration of heat capacity, for you I will ask this question. Look at this right here. This says the entropy. Okay. The entropy is equal to this. And W is the number of microstates. That's the number of possible combinations you can have. So if I put a 1 in here, what is entropy? The log of 1, folks, is 0. Okay? That means if you have only one possible way that you can have something, then entropy is 0. Okay? The only time. What is the log of 2? 0.6, 0.7, something like that. What's the log of 100? Do it. Come on. It's the natural log, okay? You just punch in 100, hit the LN button, and you get a value. You're going to have to do this on an exam, I promise you. You, write that down. This will be on the exam. Good, good, good. Okay, so we got entropy here. Log W. W is the microstates, okay? How many have done this in high school? What a bunch of babies. Well, you see, you probably took some AP class, and that's where you saw it. I, on the other hand, never took AP. So I don't even know what any of this is. I know you got to add this and get this. I can figure that out, okay? I'm smart enough for that, but I'm really not too sure what all this means. Okay, it's big numbers, okay? So, remember this, that the delta S of the universe is equal to the delta S of the system plus the delta S of surroundings. So once again, I don't like the fact that they're separated, but anyway, and this always has to be either greater than or equal to 0. It can be 0, but it can never be less than 0, okay? Entropy always wins. If it's greater than 0, it's spontaneous and irreversible. If it's equal to 0, then it's reversible and it's at equilibrium. We like this. And if it's less than 0, it's not possible. So entropy is going to tell us whether something can or can't happen. So Aaron is going to go back and ask Barb to check her email, because sometimes I don't always, sometimes the files are too big and they don't end up making it. But the lecture, this lecture, and before next lecture, the Thursday lecture will be posted, okay? Have a good day.